Good morning, everybody. That's it? Good morning, everybody. I know it's been a long week. How's build going? Yeah? Well, okay. That was pretty good. It's great. It's the best build so far this year, I'd say. So welcome to Inside Microsoft Azure Data Center Hardware and Software Architecture. My name is Russinovich. I'm the Chief Technology Officer of Azure. I've been in Azure for 8 years and seen a lot of change, going from something relatively small that nobody knew anything about to now a cloud platform that spans the world. What I'm going to do for the next 75 minutes is share with you an inside look at our data centers, both the physical aspect of our data centers as well as the logical aspect of our data centers. And I'll be highlighting, as I go through the architecture, some of the innovations that we've been working on and some of the ones that are coming, some of the ones that we've released recently, and where we're going with these innovations. The breakdown of the agenda here is I'll start with a look at the data centers themselves, how they're constructed, how we organize them within a geography, how we connect them on the network. Then I'll go into the physical network a little more deeply, show you how we wire within the data center itself and across data centers, get into some of the logical networking services, some of the cool enhancements that we've just put in recently there. Then I'll take you down a tour, little history of Azure servers as they've evolved over time. And this is kind of interesting, from the day that I started in Azure, what the servers looked like then, to what some of the servers that we've got now deployed in our data center. I'll also talk a little bit about the hardware innovation that we've got with server design and highlight some of the cool applications that we can build on top of that. I'll then transition to the compute service or services, and I'll talk about the compute architecture, and then talk about some of the things we're doing with containers and serverless and microservices. I'll talk then about storage, the logical topology architecture of storage, a cool change that we're rolling out right now with a change in the architecture to that will provide some really cool performance enhancements, and then talk about some of the forward-looking work we're doing with storage technologies to make it more cost-efficient. And then I'll switch to a little bit lower layer, the hypervisor and the operating system, tell you about what we're doing to keep the operating system more available as we roll out patches. And then I'll conclude with a look at quantum computing and what we're doing there. So it's going to be a tight agenda. I'm going to be moving very quickly through this, and I apologize, but there's just so much to show, and I have to admit that this talk is about 75 slides, which in 75 minutes is a little tight. But it started out as 115, so there's a bunch of things that unfortunately I don't have time to show you, but I'm trying to squeeze as much coolness in as I possibly can. So let's start with a look at the data centers themselves. And I'll first talk about the way that we organize our data centers. We start by defining what's called a geography, and a geography is defined as a geopolitical boundary where most of the customers within that boundary are comfortable having their data anywhere within that, from a regulatory perspective, from a compliance perspective, or just a cultural perspective of wanting their data within that boundary. More and more, these are becoming countries. And so you can see as we've rolled out our geo expansion, we've gone into places like France and made that a geo. We've gone into places like UK and Australia, and those are geos. Then we define regions within geographies. And for every geography, we have at least 2 regions. We define a region as a latency boundary. So any data centers within that region, and many of our regions have multiple data centers, have to be within 2 milliseconds round trip latency of each other, less than 2 milliseconds. So our target is less, but we guarantee 2 or less. And we do that so that you can build an application that can replicate data within that region. Then we also have this architecture where we pair regions together so that you can do a disaster recovery failover from one region to another. And we move those data centers as far as those regions as far apart as we can within the geography so that they're isolated from large-scale natural disasters like hurricanes, floods, earthquakes. Typically, that's hundreds of miles apart, which means that they're too far for synchronous replication to achieve high availability. But they're far enough apart so that these large-scale disasters you can fail away from, and potentially fail away from in a catastrophic scenario, lose a little bit of data as you're moving across. For high availability within a region, we're just started to introduce availability zones. And availability zones are multiple independent data center facilities. They're isolated from one another, both in some distance between each other, as well as they each have independent power, they each have independent connections to our network backbone. They each have independent water supplies, so they're isolated from having any correlated failures from a physical perspective between each other. And of course, because they're separate buildings, they're also physically isolated with respect to things like fires and floods within the data centers themselves. Our inter-AZ latency diameter, again, because they're in a region, is going to be in that 2 millisecond boundary. And whenever we go into one of these regions with availability zones, and our plan is to roll these out more and more, you can see that we've got I'll show you, we've got a couple in that are G8 and a few in preview, is to have at least 3 in each region. And the reason we go in with 3 versus 2 is that you can then replicate data statefully and achieve quorum. So where you have 2 out of the 3 responding and acting to a write, you know that you can then lose one of the copies and still not lose any data. We do this logical to physical mapping. So if you take a look at the region, we might have more than 3 physical AZs, like this example here. But what we do then is logically map a customer subscription, the AZs that are projected to them, to those physical AZs underneath them. And we do that so that we can shape capacity and make sure that customers can continue to expand in the AZs that they've been assigned. We can bring new subscriptions, new customers into that region, and then make available new data centers as additional AZs that are visible to them that they can grow into as well. So there's just an example of a little mapping. Here's an example of what we've got going on so far. Like I mentioned, we've got a couple in GA, we've got a few in preview, and then we have a lot of services that are zone optimized, meaning that they've been specially designed to work with this zone architecture. If you take a look at this list, you'll realize that it's the fundamental building blocks of the cloud infrastructure that are the ones that are zone specific, that you can place within a zone. And that is so that you can build a zone resilient service on top of them. So our higher level services, like you can see there, Azure SQL Database and zone redundant storage, those themselves build on those fundamental building blocks of placing a virtual machine within one zone, placing an IP address with one zone, and then that way they can do that across the 3 zones and then replicate across those virtual machines, across those networks, and have this availability such that a zone can fail and they can continue to serve writes. 2 zones can fail and they can continue to serve reads. And then you can see here some of the distance between the zones in our French region, France. There you can see Paris there faintly towards the top middle. And you can see there 2 zones south of Paris and 1 zone north of Paris. Connecting those 2 within that 2 millisecond latency diameter. Now to show some cool pictures, I like to see real stuff, and so I like to go visit our physical data centers. And the one that's closest to here is the Quincy data center that's out by the Columbia River. This is a picture of some of our data centers there. Each one of those facilities is 8 megawatts in size, so that's a total of 64 megawatts you're looking at there. The region's even larger than that. Here's another shot of additional data centers in that Quincy region. We build out over there because there's a great supply of hydroelectric power there, and so we're not the only ones that build out in Quincy. Lots of land, lots of power available there. Here's Cheyenne, another place that's great for creating a very large region, and you can see there the same data center architecture. There are 8 megawatt colos, 4 of them down at the bottom, and then there's a facility over on the right side, and then a clearing space for new ones. And this is Dublin, Ireland, another place where we've been expanding. There's different data center architectures shown in this picture. You can see over on the right side a bunch of data centers there, and one down towards the bottom. And if you look really closely, you can see the Guinness Brewery. Just kidding, you can't see that there. Here's Amsterdam, and you can see we're expanding massively in Amsterdam. There's a large area being cleared for a bunch of data centers there. That building over on the left side, that looks like it might be a data center. It's actually not. Does anybody know what that is? It's a greenhouse, and because it's the Netherlands, you have a 50-50 chance of guessing what they're growing in there. Yeah, tomatoes. That's it. So here's another shot of Amsterdam with more expansion there for data centers, a different view. You can see wind there, powered by wind farms. And then here's a look inside one of our data centers, Cheyenne. Just to avoid any confusion, the servers do not slope inside the data centers as it looks like in this picture. So speaking of natural energy, we've got a commitment to sustainability at Microsoft all up. And our data centers are no exception. We've been carbon neutral across our data center footprint since 2012. This year, we crossed the 50% natural energy threshold for our data centers. Our goal is to get to 60% by 2020, and of course, our long-term goal is to be 100% powered by wind, solar, and hydropower. And you can see some of the different kinds of energies in the different regions there that we're using. We just signed the largest solar corporate deal in history in the United States in Virginia for 275 megawatts of solar power there, just as an example of us procuring energy for the global expansion of our cloud. We're also working on trying to make our data centers more efficient in the way that they consume energy, even taking a look at very radical types of designs for the data center. As you know, data centers are powered by utility energy, utility electricity that comes into those data centers. And one of the things we realized as we looked at that architecture, first of all, utility power is not that reliable. So we have to have generators there to back up the utility power. But second, there's a whole lot of switches and transformers on the way from utility power into the data centers, into the servers. So every time you go through one of those devices, you lose a little bit of energy in the transition. So there's a significant amount of energy loss as you get down to that servers. And there's also, for any one of those switches, that's another potential single point of failure on the way to the servers. So we've been looking at using fuel cell technology, natural gas powered fuel cells. Natural gas, by the way, if you take a look at the reliability of it, it's 6 nines or higher as compared to utility power, which is significantly lower than that. So we get higher reliability for the utility natural gas coming into the data centers. Of course, we'd have redundant connections into them. But then there's no switches. The electricity is generated right there next to the servers. So there's a direct conduit from the energy source into the servers. And we expect that we can save about 50% in energy reliability and efficiency. So that's a look at our data centers. Let me talk about our inter-DC network now and what that architecture looks like. Here you can see 2 regions, A and B, and then you can see the connections out to the rest of the world, out to customers, enterprises, and enterprise VPN connections through ExpressRoute. That's all connected through our WAN, and we've got within regions, regional networks. You can see the types of services that we deliver on this network, from our DC hardware with our NICs that I'll talk a little bit more about, to the services we deliver within a region and across regions, to inter-region data center network, like DC networks, regional networks, optical modules that we use for optical switching within a region, our software WAN, the subsea cables that we've been deploying, and our internet peering sites. Speaking of that physical topology and internet peering sites, this is a look at the current state of our dark fiber backbone. So all of the traffic between our regions, between data centers, flows over our own fiber, either leased or completely owned by us. We've been investing huge amounts of capital infrastructure in building out the worldwide WAN. And last year in the fall, we announced, for example, the GA of undersea cable crossing the Atlantic called Maria that goes from Bilbao, Spain to Virginia, the first cable crossing at a different place than going from England to New Jersey, New York, a project with Facebook and Telsus, which delivers 160 terabits of capacity, making it one of the largest subsea cables ever deployed. And we've got another 2 projects that are underway crossing the Pacific as well. If you take a look within their regional network architecture, so this is the connection between data centers in a region. Like I mentioned, many of our regions consist of more than one data center, some of them up to a dozen or more data centers. And we connect them with something called these RNGs, regional network gateways, you can see. They're optically driven, so our custom optical technology to connect these different networks together. They're space and power protected, so we've got redundancy. You can see there's 2 RNG stations whenever we have one of these connections between data centers. They're physically far separated in land by several kilometers. They've got independent power and utility and water, so just like our data centers, they're protected with redundancy purposes, so we don't lose a region if one of these goes down. And then we build them in what are called t-shirt sizes. So depending on how big we expect the region to get, we can start with the small one We can expand it to medium size, or we can start with a large one. And kind of not surprisingly, as the demand for cloud continues to grow and some of our regions are getting bigger and bigger, we're realizing that we're going to probably need to XL, and then XXL, and then XXXL at some point. But that's the state of our RNGs as they connect together. The network is incredibly complicated, and one of the easiest ways to take a cloud service offline is to screw up the network. Advertise the wrong route, for example. And so whenever we add hardware, switches to our network, or new data centers, bring them online and add them into the RNGs, whenever we build out a new cluster of servers in our data center and bring those online with new top-of-rack routers, that's a reconfiguration of the network to add those servers to the route and make them visible to the rest of the world. Very complex programming. In many cases, programming like that, a small error can take down a whole region by black holing certain IP ranges. So what we've done is build our own network test service called CrystalNet. We published a paper on this in SOSPI, the Symposium on Operating System Principles, in the fall, where you can go read more about it. But this is a very accurate representation of our entire network configuration across the world. We run it in about 70 virtual machines. It reads the real configuration off our network, and then we can simulate changes and see what would happen on that. Once we've verified that the change does not impact any of the routes and does what it's supposed to do, then we can export that change and apply it. And so there's no human involvement after we've verified that the change actually works. We can even connect physical devices to this virtual simulation directly, so we can also then see how they would react and how they would interact as points along this whole network architecture. So this is, you can see we've spent over 12 million core hours in emulating our network changes over the last 6 months. And just as our networks get bigger and bigger, this is going to become something we rely on more and more. So that's a look at physical networking. Let me switch to logical networking now. And logical networking in the cloud is based on something called software-defined networking, or SDN. If you take a look at traditional IT networking, it's generally been come in the form of hardware appliances. And those hardware appliances have a bunch of different services built into them, from high-level abstractions and management APIs down to the data plane where the network traffic actually flows through the appliance itself. And the control plane is where the management APIs take and transfer those APIs into low-level commands to configure the routes on the switches. And so all of this is built in. And one of the things that we found out very early in the development of Azure, as our networks got bigger and bigger and they were growing so dynamically, is that these, to support the kind of traffic we needed, were becoming very expensive. They also were single points of failure. Or at least, if you wanted to avoid a single point of failure, you had to get 2 of them, and that was very expensive as well. So we realized very quickly that this architecture was a dead end for us from a cost and reliability perspective and a scaling perspective. So just like many others, we embarked on creating software-defined network for our data centers. In our case, if you take a look at the layers, at the very top, the management APIs to Azure are in the form of Azure Resource Manager APIs, ARM APIs. You call into ARM, and then you end up in a controller that is taking those ARM APIs, like create a new virtual network, give it these subnets, and add these virtual machines to it, and it takes those commands and takes those and configures the software-defined network, the various controllers that implement things like public IP addresses and virtual networks. And then those themselves go and program the switches, and these aren't appliances, these are the servers themselves. The switches are implemented in software on the servers. So it's a very distributed network. These 3 layers mean we can scale out each layer independently to grow. It's using standard cloud-native type of resilience architectures, so we can tolerate large-scale failures even of a whole AZ and still not have these software-defined networks go down. And then, because the switches are in the servers, they're just part of the server price, and that also scales with the scale of our servers. Just a little deeper dive in the way that software-defined networking looks. In the case of its management, the resource provider, the controllers like the regional network manager, the directory service, the software load balancer controller. The way that they interact with our servers is by orchestrating communication with the compute resource provider. So the way that network doesn't make any sense without compute to use the network. So it's really compute that kind of drives the implementation of a network, saying, I'm going to place a virtual machine on this server. This virtual machine needs to be on this subnet of this virtual network, and it needs to have this public IP address. So that dance happens with the compute resource provider talking to its own agent on the server, the network resource provider then getting commands or taking commands and sending them down to its agents down on the server to program the virtual filtering platform, the switch there you see on the lower right. That is that switch that I was talking about earlier. That bottom layer of those physical appliances now distributed into those servers. When we started with Azure, we implemented those switches purely in software on the servers. And if you take a look at what those switches do, it's a bunch of different operations. They apply network ACLs, they expose public IP addresses with load balancing, they implement virtual networks with subnets and routes configured on those subnets. And so all of that is implemented in different layers of rules that were run in the software on those servers. About 4 or 5 years ago, we went, as you'll see, from 1 gigabit networking on the servers to 10 gigabit networking. And we started to see significant CPU consumption by that logic for that switch, software-defined switch on those CPUs. We realized that not only were we burning expensive general-purpose CPU cores with the software-defined networking, we were also introducing latency to the network by all that packet processing in those servers. And if we looked forward, we saw 40